So last chapter, chapter 2, we started talking about systems of differential equations, and we looked at some qualitative techniques and a couple of limited analytic techniques for how to solve them or to study their solutions. So in chapter 3, we're going to continue to study systems, but we're going to study very specific systems called linear systems. Okay, so a linear system of differential equations has the form x prime is ax plus by and y prime is cx plus dy. So there are two linear differential equations. A, b, and c are all constants. Yep. Nope. They can be 0. They can be negative. Yep. So a, b, c, and d are just real valued constants. So this is sort of the simplest kind of system of differential equations we can study. And we're going to spend a lot of time studying them in depth because first it gives us some insight into analytic solutions, because once we get past linear, analytic solutions are going to be hard to come by. So really understanding what linear equations do will give us some insight into what nonlinear equations do. And what we do when we get nonlinear equations is we linearize them. So do you remember when you could take any curve and you could draw the tangent line, linear approximation? We did that in Calc 1. You can do that with differential equations too. So we develop all these techniques for linear differential equations because once you get something nonlinear, we just linearize it, use a linear approximation, and then use all the techniques that we're going to develop in this chapter. So the harmonic oscillator, we've talked about several different classes now, can be written as a system of linear differential equations. So my coefficient on v is a 1, and my coefficient on y is a 0. And then my coefficients on v and y have to do with the spring constant, the mass, and the damping constant. So this is just one example of a system of linear equations. And we have solved this one qualitatively and otherwise. Right, yeah. All right, so we can use linear systems, though, to model all kinds of things besides the mass on a spring. Your textbook models the profit of 2 cafes that are competing for business, but we can also use them to model love affairs. Okay? So Romeo's in love with Juliet, but in our version, the more Romeo loves her, the more Juliet feels smothered, right? And then when Romeo starts to get discouraged because she doesn't like him, he gets discouraged, he starts to back off, Juliet finds herself strangely attracted to him again. Right. So Romeo, on the other hand, tends to echo her, right? When she loves him, he loves her back, and when she grows cold, he grows more distant. So we're going to let R of t represent Romeo's love-hate for Juliet, and J of t represent Juliet's love-hate for Romeo. So positive values of R and J are going to represent love, and negative values will represent hate. We want to write a system of differential equations that can model their star-crossed love. Okay, so I'm going to have an R prime and a J prime. Okay, so how Romeo's love changes with respect to time and how Juliet's love changes. Okay, so let's go back and read. Romeo echoes Juliet. So as her feelings increase, so do his. And we can just assume the simplest model possible, proportionality, right? So Romeo will be A times J. His feelings strictly depend on Juliet's feelings. As her feelings increase, his do also. A is just a constant, like a constant of proportionality. And then Juliet is the reverse, right? As Romeo's feelings grow, her feelings decline. Right? So Juliet's feelings would be like negative B times J. Oh, times R, yeah. Romeo's feelings. Does that make sense? Okay, so so this is a model of what might of their love. Okay. And if we choose the simplest possible values for the constants, so just 1 and -1, so R prime is going to be J, and J prime is going to be -R. Just chose 1 and -1 for my constants. And I drew a phase portrait, vector field and a phase portrait. And we've got R and J. So what does this picture tell us about their romance? What's so funny about it? Yeah, so the upper right quadrant, quadrant 1, represents mutual love, right? Would they love each other? Romeo's feelings are positive and Juliet's feelings are positive. Yeah, so at least a quarter of the time, they both love each other. A quarter of the time, we have mutual hate, right? They just hate each other. And then the other the other half of the time, one loves the other and the other hates, right? Right. Yeah. In this picture, they're actually circles, and it just looks a little distorted because of the scale. But if you change the constants to have, as long as this one's positive and this one's negative, you get an ellipse. Yeah, so it's possible that their love is not always, their feelings are not always equal, whether they're both love or one's love and hate. But in this case, they are. Yeah. Their feelings are not always mutual, but equal. So we can consider the forecast for two lovers governed by a more general linear system. So Romeo, R prime is going to be AR plus BJ, and J prime is CR plus DJ. Okay, so we've got two constants. And the parameters A, B, C, and D can have either sign. And the choice of sign specifies a romantic style. Okay? So if A is positive and B is positive, so if I have R prime equals any positive number, say like 2R plus 3J, something like that, A and B both positive, what does that say about Romeo's feelings? How do they change? They grow.
They grow on their own, and then they also grow as a result.
Yes, they grow on their own, and they also grow as a result of Juliet's feelings. So grow on their own. So his own feelings for Juliet cause his feelings for Juliet to grow, right? And Juliet's feelings for him cause his feelings for Juliet to grow. Yeah, so we could name this romantic style like over enthusiastic or something, right? On their own, Juliet's feelings for him. Yeah. So Juliet's feelings for him cause his feelings to grow also. So we could call this overenthusiastic, or I don't know, you can come up with some other name. So this is like unrealistic, sure. All right, so now let's think about a different set of signs. Let's say Juliet has a negative value for C and a positive value for D. So J prime is going to be like negative 2R plus 3J, something like that. Negative C and positive D. What does this say about Juliet's feelings and how they change over time? They grow on their own. She starts to dislike him. Yeah. So let's see, we'll write it out as a sentence and then we'll try to name it. So Juliet's feelings grow on their own. But they decline as Romeo's feelings grow, right? As Romeo loves her more, she backs off. So, or yeah, as he hates her more, she's gonna love him more. Yeah. So what could we name this? What romantic style could we give this name? Unhealthy. I like that. I like that. Unhealthy. So for some reason, her own feelings, as she loves Romeo, that causes her love to grow. But Romeo loving her back causes her love to die. Right. So yeah, that's a little unhealthy. There's two other romantic styles. I want you to, in your groups, what are the choice of signs that define them? So we did both positive. We did one positive, one negative. So there's two more. And how would you describe them? Describe them and give them a name. All right. So let's just discuss Romeo. It's the same for both of them, but if Romeo has, what did we do? We did C negative, D positive. So if we do A positive, D negative, oops, B negative. Right, so R prime is something like 2R minus 3J. So what does that say about Romeo's feelings? How do they change over time? Decrease when Juliet loves him. Yeah. So this is nearly the same as the other one, right? Is this exactly the same? The unhealthy male version, yeah, okay. Because we switched the variables, yeah. All right, so if I switch it, because this is the same, like negative 2R plus 3J. So this would be A negative, B positive. Okay. Right. So his own feelings for Juliet cause him to dislike her more, right? Like the more, if he has feelings for her, it's like he hates himself for that, right? Yes, right. It makes him feel uncomfortable that he has these feelings, so they decline, right? But when Juliet loves him, that spurs on his love. So yeah, what did you, he's a commitment phobe, right? we, Sure, you can make that argument, yeah. Right, right. So let's see if I can write out a sentence that says this. So So Romeo's feelings for Juliet naturally decline, right? If his feelings, if his love were only based on his own love for Juliet, this would be an exponential decay, right? So, right. True, right, yeah. So they naturally decline, right? Juliet naturally decline, but Juliet's feelings spur him on, right? So as Juliet loves him more, his love for Juliet grows, and as Juliet hates him more, his hate for Juliet grows. So he just echoes Juliet's feelings, but then he has this natural inclination to stop loving her on his own. Right. Is it what? Yeah. All right, and then we have one more where they're both negative, right? So Romeo would be like negative 2r minus 3j. So Romeo's feelings for Juliet naturally decline, right, on their own, and they lessen with Juliet's love for him. Right, and as she hates him, he loves her more. Right. So yes, as he hates her more, he starts loving her more because his own feelings cause the reverse in growth, right? Do you think it'll approach 0? I don't know what it's going to approach, but right, right. So let's see. So Romeo's feelings change to counter what he's currently feeling, right? So because this coefficient is negative, if he loves her, the change is he loves her less. And if he hates her, the change is he hates her less, right? Yeah, so Romeo's feelings change to counter his current feelings. They counter his current feelings and they counter Juliet's current feelings. So if Juliet hates him, he starts to love her. And if Juliet loves him, he starts to hate her.
But if he starts to love her, Juliet hates him, then he also starts to hate her
because he counters his own feelings. Yeah. Yeah. To counter his current feelings and to counter Jay's current feelings. So, I mean, what could we call this kind of love? Crazy. Sure, we'll call it crazy. So it's entertaining to name the different romantic styles and to predict the outcomes of various pairings. So for example, can we pair a cautious lover who what did we call this? A negative, B positive. Unhealthy, yeah. Can we pair unhealthy with overenthusiastic, right? Will they find love? Will they eventually be able to find mutual love? Like what happens to them if they get together? So yeah, that's the solution to the system, yeah. So this and other pressing questions will be answered using the tools we develop in Chapter 3. And I can hardly wait to find out either. All right, so first, as always, we have to start with some new notation to develop the tools that we're going to need. So we can write a linear system, x prime equals ax plus by, and y prime equals cx plus dy, much more efficiently using vector and matrix notation. So who had linear algebra? Okay, less than half. Okay, so I'll go over all of it. So we use this, we can write this using vector and matrix notation. So A is the 2 by 2 coefficient matrix. So you just put big brackets, 2 entries across, 2 entries down, and you just put in the coefficients A, B, C, D. So we call that the coefficient matrix. And Y is going to be a column vector of dependent variables. So that's the X and the Y. So again, I'm using bold, a bold letter to represent a matrix or a vector, and unbold to represent just scalars, numbers. So let's see what happens when I take the product of A times Y. A, the matrix, so bold, times Y, the vector, bold. Okay. So A is A, B, C, D, and Y is X, Y. Okay, so who knows how to multiply matrices? Calculators do. Okay, a couple people. All right, so the way you multiply two matrices is you multiply each row in the first matrix times each column in the second matrix. And what it means to multiply a row times a column is, imagine you pick up this whole row. You just pick it up off the paper. I'm holding it right here. Turn it on its side. Lay it on top of this column. The A would be on top of the X and the B on top of the Y. Multiply the things that line up and then add the entries. Okay, so this is going to be AX plus BY will be the first entry in my answer. Okay. And then I take my next row in this matrix, pick it up, turn it on its side, lay it on top of the vector. The C and the X line up, the D and the Y line up. You multiply what lines up and add them together. Okay, so when I multiply the coefficient matrix times the vector of dependent variables, when I multiply them together, I get AX plus BY and CX plus DY. Those are the right-hand sides of my two differential equations. So I'm not going to, spend a lot of time talking about matrix multiplication because it gets more complicated when you do like bigger matrices and stuff, but we're only ever going to do 2 by 2 matrices times a column vector. So if you can see that this equals this, you're good. Okay. All right, so that means that I can rewrite the system as A times Y. Okay, so Y is the column vector of dependent variables x, y. That means bold Y prime is a column vector of the derivatives of the dependent variables x prime, y prime. So bold Y prime equals bold A times bold Y. Right, because Y prime is x prime, y prime. A is A, B, C, D. And Y is x, y. So this is a nice little shorthand for writing the system, is that now I can write it like that. All right, so I want to write this system in matrix form. You try it. See if you can take what I just showed you and write it in matrix form. All right, so I'm going to write this as x prime, y prime in a vector. That equals my coefficient matrix, -1, 1, 0, 3, times my vector of dependent variables x, y. And then if I want to name my vectors and matrices, I could call this capital Y, bold, prime. That's what I'm going to name this vector of dependent variables derivatives. It's sort of an arbitrary choice. We could name it anything we want. Part of why we do this is because once we write it in vector notation, it looks like a one-dimensional differential equation, which we often write as y prime equals, right? So that's kind of why we call it y, but it's arbitrary. So -1, 1, 0, 3 times y. Personally, I like this because it reminds me what why I'm writing it in vector notation. You can clearly see that it's a system of x prime and y prime. All right, so now here's a linear system represented by a matrix equation. Convert it back to two equations. X prime equals y prime equals. All right, so they've given us y prime equals 3, -9, -7, 5 times y. And the y prime and the y are bold, so we know that those represent vectors. Okay, so y prime is really the vector x prime, y prime. And then I've got my matrix 3, -9, -7, 5 times my vector xy. Why? Yeah. The reason is that when I write a one-dimensional differential equation, I often use y as my dependent variable. So the reason that we like to compress a system into matrix notation is to make it look like a one-dimensional system, and then we can apply times y, yeah. So that's why we do that, because it echoes what a one-dimensional system looks like. Yeah. But yeah, V would make more sense to be like, this is a vector, right? Okay, so I just rewrote my vectors. This is still not written in x prime, y prime. So x prime equals what I get when I multiply this matrix times this vector, right? So you take A times B, sorry, the A and the B, the first row of the matrix, pick it up, turn it on its side, put it on top of the xy, multiply the things that line up. So I get 3x and -9y, and you add them together. Right, and then you do the same thing for the next row. So y prime, this entry, is equal to this row times my column vector, -7x plus 5y. So there's my system. You don't have to do the multiplication out every time. You can kind of jump right to, this is A and B, and the system is AX plus BY, and this is C and D, and Y prime is CX plus DY. So you could just remember how they relate, but it's kind of important to know that this is why we write it in matrix form, because the multiplication brings you back to the system. All right, so we're going to start our study of linear systems by looking for the simplest solutions, which are equilibrium solutions. So equilibrium solutions have to satisfy both x prime equals 0 and y prime equals 0. Ax plus by equals 0, cx plus dy equals 0. This is how you write that in our vector matrix notation. But in essence, we have a system of equations to solve. Ax plus by equals 0 and cx plus dy equals 0. Two equations, two unknowns, x and y. Let's solve it. So I pick one equation. I'm going to solve it by substitution. And I'm going to solve for one of my variables. Let's say I solve for x. That would be negative b over a times y. Then I take that value for x, plug it into my other equation. So I have cx plus dy equals 0. So c times negative b over a y plus dy equals 0. Use an old technique that you probably learned in college algebra. When you have fractions, just get rid of them, right? Multiply everything on both sides by a. So I have negative bc times y plus ad times y equals 0. Multiply every term on both sides by a. So now I could factor out a y. So I have y times ad minus bc equals 0. So either y equals 0 or ad minus bc equals 0. Okay. If y equals 0, then x also equals 0, right? If I plug a y equals 0 into this equation, x also equals 0. So one equilibrium point for any linear system is going to be 0, 0. 0, 0 will always be an equilibrium point. So it's right here. And the only way I'm going to have another equilibrium point is if that equals 0. I'll only get another equilibrium point if AD minus BC is 0. Because these are all constants. There's nothing to solve here, right? Those are just constants. And in the event that AD minus BC is 0, we'll find another equilibrium point. So that value AD minus BC is a particularly important number that's associated with a 2x2 matrix. It's called the determinant of the matrix. It's denoted det of the matrix A. AD minus BC. So if you took linear algebra, you should be pretty familiar with determinants. Okay, so our conclusion, based on trying to solve that system, is that the origin, 0, 0, is always an equilibrium point of any linear system. I should add the word linear here. Of the linear system. We call this the trivial solution. Okay, x equals 0 and y equals 0. If Romeo and Juliet both start out completely indifferent to each other, their feelings never change. So we call this the trivial solution. And then the system has a non-trivial solution, non-trivial equilibrium points, if the determinant of A equals 0. That's the only time you'll get another equilibrium solution, if AD minus BC is 0. All right, so I want you to take 10 minutes and work through this example in your groups.